Hi guys, welcome back to old subscribers. Hello to any new ones. Good to see you guys. This is mostly for year 10, and what we're looking at today is the energy change in reactions, how we calculate those energy changes, and this is higher tier. It's topic 5 and it's for part 1, endothermic and exothermic reactions. So we'll be looking at today the energy changes that are involved in making and breaking bonds in a chemical reaction. We'll be looking at calculating the energy released when chemical bonds are made and how to calculate the energy needed to break chemical bonds. We're also going to work out how to calculate the overall chemical change, and this is the most important part of the lesson, in a chemical reaction. And then we'll have a look at the differences in energy change between exothermic and endothermic reactions. Now this is higher tier, it can get quite difficult, so please don't be afraid to put the video on pause, replay bits, and maybe check out some other good resources like GCSE Bite Size so you get it from a couple of different ways. Energy and enthalpy, we need to define these things. So to calculate the energy changes, we need to know how much energy it takes to break a bond, and that's the information you will get given in an exam question. When a bond is formed, it releases the same amount of energy that it would take to break it. So when we make a bond, it releases the energy that it takes to break it. So they are the same, they're interchangeable, these bond energies. So if I want to make, say for example, a carbon-hydrogen bond, I would release on making that bond the same amount of energy that I would have to use to break it. So it's exactly the same for the purpose of these calculations. You will also sometimes see bond energies described as something called bond enthalpies. It's exactly the same, it's just basically another word. Bond enthalpy basically just means the amount of energy it requires to break a bond. Okay, a specific bond. In all chemical reactions, firstly, the first thing that happens in all chemical reactions is energy is supplied to break the bonds in the reactants. So whatever you have for reactants, firstly, energy must be used to break those bonds. Secondly, energy is released when the bonds in the product are made. Now this is just for the purpose of these calculations. You really need to be thinking about this. So, breaking bonds needs energy, making bonds releases energy. So that's a little summary of those parts. So how do we calculate the overall energy change of a reaction? Well, let's look at the steps that you're going to need to do. Firstly, you're going to have to read or work out the displayed formula of all species, and we'll have a look at some examples of this in a minute, so don't worry too much about what a displayed formula is yet. Then we're going to count the number of bonds of each type we have, and we're not going to forget to include the number of molecules we have. For example, if we have a very, very simple compound, say HCl for hydrogen chloride or hydrochloric acid, HCl, we've got one bond there between the hydrogen and the chlorine. If we've got in our chemical formula it says 2HCl, we've now got 2 hydrogen chlorine bonds, and we mustn't forget that in our calculations, and again we'll see that in a minute. Then after that, step 3, we're going to use the table of bond enthalpies that you will be given to work out how much energy is needed to break the bonds of the reactants. Then we can use the table of bond enthalpies to work out how much energy is released when making the product bonds. And then we can use this formula. This is an important formula. You definitely need to make sure this is recorded somewhere with a big box around it. The overall energy change is equal to the energy of the bonds that we've been breaking, take away the energy of the bonds that we are making, or the energy inside those bonds, or the bond enthalpy. So you might also see it, the overall energy change is equal to the enthalpy of bond breaking, take away the enthalpy of bond formation. If the overall energy change is negative, then the reaction is exothermic. That is showing us, if the overall energy change is negative, that there is more energy in making those bonds, so that energy is being released to the surroundings, so it's exothermic. If the overall energy change is positive, then obviously the reaction is endothermic. It's the opposite way around. So let's have a look at an example reaction. The combustion of ethene, which has got a chemical formula of C2H4. It's an oxidation reaction, so we're going to be reacting with oxygen. And the word equation is ethene plus oxygen makes carbon dioxide plus water. And I'm sure you can now turn that into a simple equation, so put the video on pause, give yourself a little practice putting that into a simple equation. So you should have got C2H4 plus O2 makes CO2 plus H2O. Now we need to balance this, so again put the video on pause, give it a go and try balancing it. I do now have a video for balancing equations, so if you wish to go and do a little bit more work on that, please go and find that video. I'll try and remember to post a link and watch that as well. But the balanced equation is we get 1 ethene, C2H4 plus 3 O2 makes 2 carbon dioxides plus 2 waters. Okay, and that's all balanced now. My first step in doing this was I started off balancing the carbon, so I knew I needed a 2 in front of the CO2 to give us 2 lots of carbon. Then I wanted to balance the hydrogens. I've got 4 on the reactant side and only 2 on the product side at first, so I had to make 2 H2O. And then it was just a matter of balancing the oxygens. So energy is needed to break the bonds in ethene, and also energy is needed to break the bonds in oxygen on the left hand side of that arrow, are reactants. And the energy is released when the bonds in carbon dioxide and water are made. And because this is an exothermic reaction, all combustion reactions are exothermic, we know that the energy released when we're going to make the bonds is going to be greater than the energy required to break the bonds in our reactants. So we're expecting our energy change to be negative. So let's have a look at this. Let's calculate first the energy needed to break the reactant bonds. And again, we've got a balanced equation. So we need to know the displayed structure of the reaction. And this reactant, often this will get given to you in the question, the exam question. And this is what they look like. So on the left down here at the bottom, we've got our ethene displayed structure. So we've got our 2 carbons, our 4 hydrogens, and we can see the carbon has got a double bond to the next carbon, and each carbon is also bonded to 2 hydrogens. Oxygen, very nice and simple. We've got our 2 oxygen molecules with a double bond 2 oxygen atoms with a double bond in between them. So that's the first step. We've got that. The next step, we need to count the number of each bond we have. So we'll start off with carbon hydrogen. We've got 4. 1, 2, 3, 4 carbon hydrogen bonds. Our carbon-carbon double bonds, we've got 1. And our oxygen double bond, we have 1 per molecule. But if we look very carefully up here, we've got 3 lots of oxygen. So we've got 3 lots of this. So we've got 1, 2, 3 oxygen double bonds. Okay, stop and have a little think about that. We've got 3 O2, so we must have 3 of the oxygen double bonds. Okay, so 3 bonds. Okay, so now the next step. We've got our bonds. We've got 4, 1, 3. I've simplified it there now. The next step is we're going to compare the bonds to a table that you will be given and work out how much energy in total is required to break those bonds. Okay, so start off with the carbon-hydrogen bond, and you can see here we've got our bond enthalpies values all listed there. So for our 4 CH bonds, we've got 4 times 413, which is equal to 1,652 kilojoules per mole. So we need that amount of energy to break the 4 CH bonds that we've got in ethene. Next up, our 1 carbon-carbon double bond requires 602 kilojoules per mole. We can read that straight away. And now we've got our 3 oxygen double bonds. And again, we read the table and we found out 1 oxygen double bond has an enthalpy of 498. So we need 3 times 498, which equals to 1,494. That's the amount of energy for each of those type of bonds. We've now got to add that energy together. Okay, and when we do that, we add all those bond enthalpies together, we get 1652 plus 602 plus 1494, and that equals 3,748 kilojoules per mole. So the amount of energy to break all the reactants is 3,748. I hope so far you're following this. Now we need to calculate the energy released when making the product bonds, and this is done in exactly the same way as breaking bonds. Everything is exactly the same. So here are our displayed formulas. Carbon dioxide, CO2, water, H2O. So the water is a single OH bond. So we've got single bonds there, and the carbon and oxygen is a carbon double bonded to two oxygens. So it's got two carbon oxygen double bonds per carbon dioxide molecule and two HO bonds per water molecule. So there are our bonds that we have. How many do we have of each? So on the product side, how many of each of these two types of bond do we have? Put the video on pause and work it out for yourself. And now we'll have a look. So we've got two carbon oxygen double bonds per molecule. We've got two molecules. It tells us in the symbol equation up at the top, 2 CO2, so we've got two lots of this. So we've got 2 times by 2, which equals 4 carbon oxygen double bonds. For our water bonds, our HO bonds, we've got 2 HO bonds per molecule, and we've got 2 molecules, so again we've got 2 times 2, which equals 4 hydrogen oxygen bonds. See if you can work out the next step. If you got it, it's to calculate the bond enthalpies of these bonds, and that is quite simple. So again, put the video on pause, give it a go. We've got 4 carbon oxygen double bonds. Each carbon oxygen double bond has got an enthalpy of 805, so we do 4 times 805, which equals 3,220 kilojoules per mole. We have 4 hydrogen oxygen bonds. Each hydrogen oxygen bond is 464 kilojoules per mole. So again, we do that sum and we get 1,856 kilojoules per mole from the hydrogen oxygen bonds. Now see if you can work out what our next step is. Hopefully we add them together. Nice and simple. 3,220 plus 1,856 is equal to 5,076 kilojoules per mole, and if you can remember, this is a fair amount more than the amount of energy it required to break the bonds in our reactants. So what's our next step then? Our next step to calculate the overall energy is to take the energy required to break the reactant bonds, take the energy we release when we make our reactant bond, our product bonds, add it into the formula that was in step 5. So we do energy of the bond breaking, which is 3,748, take away the energy of bond making, so 3,748, take away 5,076, and we get an answer of negative 1,328 kilojoules per mole. The negative shows us it's exothermic, and therefore we know we're right. Okay, another example. This is one that I've seen in an exam before. It's combustion of methanol, or well, actually they use it in a different example, but it's combustion of methanol. We'll keep it simple. So here in the question they have given us the displayed formulas, and you will notice it says 2 of this molecule, 3 oxygens, 2 carbon dioxides and 4 waters, and then we get given the bond energies in kilojoules per mole rather than the bond enthalpies. It's the same thing, just a different word. So to work it out, step 1, we're going to work out what reactant bonds we've got. We've got 6 CH bonds. We've got 3 per molecule of methanol, but we've got 2 methanols, so we've got 3 times 2, which equals 6 CH bonds. We've got 2 carbon oxygen bonds because we've got 1 per molecule, 2 molecules. We've got 2 OH bonds because we've got 1 in the molecule, and we've got 2 molecules. And last of all, we've got 3 double bond oxygens. So work out the energy in those reactant bonds. We've got 6 times by the energy of the CH, so 6 times 412, plus 2 times 360, the energy from the 2 carbon oxygen bonds, plus 2 times 464 for the OH, and plus 3 times 498, the oxygen double bond to the oxygen, gives us a total of 5,614 kilojoules per mole. So now we need to move on and work out what our product bonds are. And our product bonds are, we've got 2 carbon oxygen bonds per molecule, or carbon oxygen double bonds I should say, per molecule. We've got 2 molecules, so we've got 4 in total. This time we've got 4 water molecules. Each water molecule has 2 hydrogen oxygen bonds, so we've got 8 hydrogen oxygen bonds in total. So now we can work out the energy in those product bonds. So 4 times 805 to work out our carbon dioxide, and then 8 times 464 to work out our waters. And when you add that together, you get 6,932. Next step, nice and simply, we add this in to our equation. So energy change is equal to 5,614, our energy in our bonds broken, take away 6,932, energy in our bonds formed, so reactants bonds, product bonds, gives us minus 1,318 kilojoules per mole. Now, a slightly trickier example that has come up in exam questions is this one here. We've got the reaction between methane and bromine, and this time we are given the values of CH, the values of Br and Br, the values of CBr, we're not given the value of CBr, we're given the value of HBr, and we're given the overall energy change, and we've got to calculate X. And it's just like any algebra equation. It's rearranging, subtraction, and addition, and maybe a little bit of multiplication as well. So again, we do it exactly the same. We work out our reactant bonds. So we've got 4 carbon-hydrogen bonds here, and we've got 1 bromine-bromine bond here. So we've got 4 times 412 for our carbon-hydrogen bonds, plus 193 for our bromine-bromine bond, and our bonds broken, our reactant bonds, has a total energy of 1,841 kilojoules per mole. Now our product bonds, we've got 3 CH bonds this time, 3 CH. We've got 1 CBr, or carbon-bromine, and we've got 1 hydrogen-bromine bond. So our 3 CHs is 3 times 412, just like it was in the reactant side. Our 1 CBr, we don't know what that is, that value is X, and our 1 HBr is 366, okay, read from the table. First thing I would recommend doing at this stage, the way I would do it is I would work out everything in the products, so work out the total energy of the products by adding everything that isn't X together. So we've got 412, 3 times 412 plus X plus 366, so do your 3 times 412, add 366 to that, and that gives you a total energy of the products of 1,602 plus our mysterious X. Now we can place this into the overall equation. We've been told the overall energy change is minus 51, so that goes in overall energy change minus 51 is equal to 1,841, which is our bonds broken, our reactant bonds, take away this here for our products. So take away 1,602 plus X. So tricky, maybe a little bit trickier. But again, it's just like algebra. At this point, it's just like the algebra you do in a maths lesson and have been doing in maths lessons for ages. It's really, really simple addition and subtraction. So firstly, I'm going to simplify the equation by doing 1,841 take away 1,602, and that gives us minus 51 is equal to 239 plus X. Nice and simple. Next step, I'm going to take 239 away from each side to leave just X by itself. So we have minus 51 take away 239 is equal to 239 take away 239 plus X. So that means that minus 290 is equal to X. So the value of X in here is really 290 kilojoules per mole. Okay, and that is how you would work out this question. It's just algebra, it's just the rearranging. So summary time then. Energy is required to break a bond, chemical bond. Energy is released when we make a chemical bond. In an exothermic reaction, the energy change, overall energy change, is always negative, and in an endothermic one it is positive. That is showing that in an exothermic reaction our products release more energy when we're making those bonds than is required to break the bonds of the reactants. The equation of overall energy change is equal to the energy of bond breaking, take away the energy of bond making. You might also want to put that as energy of reactants, take away energy of products, like we have here. So energy of reactants, overall energy change is equal to the energy of reactants take away the energy of the products. All simple equations must be balanced, so do give them a check. If they don't look like they've been balanced by the exam board, give them a check. And don't forget to include the number of molecules in your calculations of how many bonds you have. Okay, now it's a bit tricky to get the grasp of at first, but believe me, it's just like riding a bike, it's just like balancing equations, it's just like doing moles. With enough practice it'll become second nature, and when it comes up in an exam you won't bat an eyelid and you'll pick up the 3, 4, 5 marks or however many will be in the question about it. Please, if you've got any questions, do ask me. Rewatch the video just to make sure that you've got it all. Try working your way through the examples as well alongside with me and follow the maths that's going on. It's just maths here, it's just algebra essentially, and it's quite simple. I'm not asking you to do anything massively difficult, so just be aware that you will get it with a little bit of practice. Okay, please remember to like and subscribe if you've not already done so. Please as well do ask me questions if you have any problems with this. If there's any issues for you, do ask those questions. I hope to see you in a video soon. Take care guys, bye bye.